We've just seen how to make an X-ray beam, and lastly today we're going to see what happens when we fire that beam at some material. And what happens is that not all of these X-ray photons are going to make it out the other side. Some are going to be absorbed and some are going to be scattered off in other directions. So the beam that comes out is weaker than the beam that went in. We have a very fancy name for this. It's called X-ray attenuation. The X-ray beam attenuates as it passes through the material. But how much weaker is it? Well, if the intensity of the beam that comes out is I, and the intensity of the beam that went in is I0, then we can calculate it with this formula. The X-ray actually attenuates exponentially. So the X there is the thickness of the material. It makes sense that the more material you pass through, the more the beam will attenuate. The intensity and the initial intensity we've already seen there, and those are measured in watts. And then the mu there is a constant, and it's called the attenuation coefficient for the material, and it depends on the material and actually also on the energy of the X-rays. Okay, if X is measured in meters, then the attenuation coefficient is measured in meters to the -1. But often you'll see X measured in centimeters, and then the attenuation coefficient needs to be centimeters to the -1. It doesn't matter as long as when you multiply them together, there are no units up there. Okay, but what's actually happening to the X-rays in here to cause them to not be in the beam when it comes out again? Well, that is the second part of the story here. So we've got 4 things that can happen to our X-ray photons as they pass through a material that stops them coming out the other side again. 2 of them are scattering, so that means our X-ray will come out, it just won't come out in the original beam. And 2 of them are absorption, so that means the X-ray disappears. Okay, in simple scattering, this is where you have a relatively speaking, a low energy X-ray. And all that happens is that it gets deflected a little bit. And the energy of the scattered X-ray is the same as the X-ray that came in. In Compton scattering, something very strange indeed happens. This is for relatively large energy X-rays. So in comes an X-ray, and you don't really need to understand why, but basically it behaves as though it was a particle, and it sort of collides with one of the atomic electrons. And imagine if you had 2 particles colliding, what happens is that this X-ray gives some of its momentum to the electron. So then what happens is the X-ray is scattered, it comes off, but now it has less momentum and less energy than it had before. And this is very strange. This is your X-ray photon behaving like a particle. Back in more familiar territory again, the photoelectric effect we know all about. Here we have medium energy X-rays coming in, and if they have just the right energy, they can hit an atomic electron and be absorbed. The atomic electron jumps up to a higher energy level, etc., etc. But the important thing for what we're talking about here is that the X-ray is gone. It's been absorbed. And lastly, for very high energy X-rays, pair production can happen. Now here, our X-ray photon is actually interacting with the nucleus. You don't have to remember that, but that's what's going on. It's actually interacting with the nucleus. Anyway, what happens is the X-ray photon disappears, and in its place we have an electron and a positron. So there's an electron, a new electron, and a new positron created, and off they go. So we've created an electron-positron pair from the energy that was the X-ray. So those are our 4 mechanisms. These are the 4 ways that X-rays can be either absorbed or scattered out the beam. And so here's a great big X-ray attenuation question to finish. And let's see how you got on. So it's only 2 marks for describing the Compton effect here, Compton scattering. So that's quite good. You don't have to remember in too much detail. So you get 1 mark for saying that an X-ray photon interacts with an electron in the atom, and a second one for saying that the electron is ejected and the energy of the X-ray photon is lower. For the next part, we're going to use the attenuation formula, and just to note here, you've probably spotted I made a mistake earlier. I said intensity was measured in watts. It's powers measured in watts. Intensity is measured in watts per metre squared, so please excuse me for that mistake. On we go. So the intensity formula is that one here, and putting our numbers in, we get this. Remember, don't round because it's a show that question. And there's a really nice question to finish with here, showing you exactly how this is being applied. So we're working out how long you need to fire these X-rays at the tumour in order to kill it. Okay, so we've got the cross-sectional area of the beam, and then we're looking at energy. So we've got intensity, area, energy, time. Hopefully, when you write all those down, you realise that the connection is power. So first of all, we can take the intensity that we worked out in the previous part of the question and the area there. Don't forget to carefully convert millimetres squared to metres squared. And that allows us to work out the power of the beam. So that, remember, is the number of joules per second being delivered by the X-ray beam. But we're told only 10% of the energy from the beam is actually absorbed, and so that means that the power absorbed by the cancer cells is only going to be 10% of what we've just worked out. And lastly there, we use our familiar formula for power and rearrange for time, and then that gives us how long we need to kill the tumour.